Good day, ladies and gentlemen. Today I want to finish up repeated addition patterns with our recursive arithmetic sequence form or formula. Many people start the investigations with this particular topic, but it seems a little archaic or old school for me, so I finish it here. Repeated addition patterns, otherwise known as linear equations, are first-order polynomials. We know that because the exponent for x is just 1, it's being raised to the power of 1. Once we start to change the exponents, the relationships will change dramatically. Because the exponent is being raised to the power of 1, the patterns are increasing or decreasing by amounts that are being repeatedly added over and over again. You got to remember, although it appears as multiplication, multiplication is just repeated addition. In all formulas for repeated addition patterns, the constant average rate of change is the same. It's going up by the same amount or down by the same amount over and over again. All repeated addition formulas come from the slope of a line formula. If you take the slope of a line formula, m equals a change in y with change in x, and cross multiply, the first formula we get is the point slope formula. In the point slope formula, we're able to investigate a repeated addition pattern from any point in time. We identify that as the initial point. In the formula, it shows up as the opposite of the amount that appears added or subtracted to y as the measured amount in time, at some point in time, and we're seeing the opposite of the time it was measured. It's always important to understand how to pull that information out of the relationship. If you were to take the point slope formula and appropriately solve it using algebraic steps, at time 0, what you get is slope intercept form. Y equals mx plus b, the most popular form or formula for all linear relationships. I like to think of it as y equals a plus or minus b times x, because a would give us the initial amount, the value at time 0, and it would tell us how much it's increasing or decreasing by, or more specifically, what we're adding or subtracting over and over again in this repeated addition pattern. Remember, subtraction is the same as adding the opposite. The rate of change m is telling us how much it's going up or down each time over and over again. B, the beginning amount, is the value at time 0. It's the initial amount in all repeated addition patterns in slope intercept form, again, evaluated at time 0. That would be right now, not suspecting that we're looking at a point in the future and working backwards, or a point in the past and working forwards, just right now at this particular time. A formula we didn't get a chance to look at is called standard form or intercept form. And standard or intercept form says ax plus by equals c. We'll take a look at that later on when we have to do more work with x and y intercepts. Yesterday we talked about repeated addition patterns as explicit in explicit arithmetic sequence form or formula. And in explicit arithmetic sequence form or formula, the word explicit simply means with great detail. So a sequence formula that has great detail in it is really just similar to y equals mx plus b. The only real differences are that we're calling y a sub n. Remember, a subscript is just a position in a formula. In other countries, n is the number that we're looking for as opposed to y. A sub n means the amount at time n, a standing for amount. The amount at time n is the same thing as y. Y tells us what the measured amount is at some point in time, and the amount at time n does the same exact thing. A sub 0 tells us the amount at time 0, which is exactly the same as the y-intercept, the value at time 0. D is the common difference. It's what we're adding or subtracting over and over again. And n is the number of times that those repeated additions or subtractions occur. So it is pretty much identical to y equals mx plus b. We've just used different names for y, m, x, and b. Y, once again, is the amount at some number of times of repeated additions. M, the amount that we're adding over and over again, our constant rate of change, is known as d, the common difference. X, the number of repeated additions, is known as, in this instance, n for the number of repeated additions, and b, the beginning amount, we call the amount at time 0. So if you to transpose y equals mx plus b into sequence formula, remember, we're just changing y to a sub n, the amount of time n. We're changing m, the amount that we're repeatedly adding over and over again, the rate of change, to d. We're calling it the common difference. Instead of calling it x, the amount we don't know, or the number of repeated additions, we're actually calling that m for the n for the number of repeated additions. And rather than calling b the beginning amount, we're calling it a sub 0, the amount of time 0. It actually makes more sense, and most of the world actually uses that formula, as opposed to y equals mx plus b. The explicit sequence formula goes a lot further in mathematics. There's so many more things we could do at other levels of math. So going completely backwards now, I'm going to show you where most people start, which is called a recursive arithmetic sequence. The word recursive means reoccurring or over and over again. I like to call this the caveman formula. The caveman formula because it requires a lot more steps to kind of understand, even though it's supposed to be easier to work with. So a sub 0 is still going to represent the amount of time 0, but in many instances we may prefer to call it a sub 1, the amount of time 1. There are certain instances in mathematics where we're not investigating according to time. 90% of the time the x-axis is time, but not always. Sometimes when we're doing an investigation, we're simply counting things like the amount of cars in the parking lot or the amount of students in the class. The initial amount, the first car or the first student, is the first one. It's 1, it's not 0. So in those instances, it's going to be a little different. We're going to have to know that what we're looking for is based on the fact that we're starting at 1 rather than 0. And that's going to change our interpretation a tiny bit. In a recursive formula, a sub n still means the amount of time n, but a sub n minus 1 simply means the previous amount in the formula. And what the formula will suggest to us is that if we know any starting amount, to find any new amount, we simply have to take the previous amount and continue to add to it over and over again. A sub n means the value of the previous amount. That's the trickiest thing to wrap your head around, and that's where most students have difficulty. In addition to that, there's other ways to present the formula. We could call a sub n plus 1 the new amount. It's the amount past time n, the next one, and then a sub n would be the amount that we're investigating and we're going to add to over and over again. So the formula can have a bunch of different presentations that look very similar and can ultimately cause some confusion, even though it's supposed to be easy to do. If you look backwards algebraically, n is the value at right now. N plus 1 would be the value 1 unit of time or 1 addition forward into the future. N plus 2 would be 2 additions or 2 repeated additions into the future, 2 times into the future. N minus 1 would be the amount prior to time now, and n minus 2 would be the amount prior to that. Let's take a look. If you turn the page, we've got a set of relationships we'd like you to investigate, and in your investigations in these repeated addition patterns, we'd like you to begin by writing them in slope-intercept form. We would then like you to write an explicit arithmetic sequence based on the work we did yesterday, where we're simply substituting a sub n in place of y, we're substituting a sub 0 as the initial amount, d is the common difference, and n is the number of repeated additions. The only real substitutions we're going to have to do are replacing y with n sub n and replacing x with n, the number of repeated additions. Other than that, everything else will be the same. In the explicit arithmetic sequence form, we can consider the fact that maybe we don't want to describe it at time 0, and if we describe it at time 1, we're going to have to change the formula a tiny bit. By suggesting that the amount that we're investigating is the first amount, it's the first child in the class that we're counting, or it's the first car in a parking lot, the number of repeated additions d is going to happen one less time than the actual amount of repeated additions we'd like to have, because by starting at the amount of time 1, we've already actually put in one of the repeated additions. So it'll be a little bit different when we try and recognize the relationship or present it as a repeated addition pattern starting at time 1 as opposed to time 0. Lastly, we're going to have you practice this recursive arithmetic sequence formula. And in this subscript presentation of an arithmetic recursive sequence formula, you're going to need 2 equations to describe it. The first equation is going to tell you where the pattern starts. You'll say that it's either time 0 or you'll say it's position 1. The next equation will give you a set of rules, and the rules will tell you how to find each new amount in the pattern over and over again. It's a little annoying because you'd have to use this pattern over and over again to find the next amount rather than just substituting in for any number of repeated additions you'd prefer, as we do with slope-intercept form and its very closely related sequence form. Okay, let's take a look. So in the very first question, we see a number pattern that goes from 160 down to 147, down to 134, down to 121. What we want to do right away is determine the common difference. How is each number in the pattern different than the one prior to it? Technically, in order to determine the actual amount of the increase or decrease in the number pattern, you're supposed to take each measured amount and subtract out the prior amount. So we're supposed to take 147 and subtract out 160 to see that there's a difference or a decrease of 13. We're then supposed to take 134 and subtract out 147 and see that once again there's a difference of 13. And if we continue to do that, we'd find out that the common difference is 13. In sequence relationships, we call that D, the common difference. The common difference is the exact same thing as M, the rate of change, when we interpret it in a slope-intercept presentation. So they mean the same thing. Once we know the common difference, we simply want to identify the beginning amount. Normally, the beginning amount in a linear presentation would suggest that B equals 160. It's the value at time 0. But you can imagine how that'd be a little confusing, because why are we calling the first thing we see time 0? Often we would suggest that it is either the amount at time 0 in sequence notation, 160, or if we want it to be more accurate because we were counting things, cars or persons, we might say that it is the amount in position 1. And that would actually be a little more accurate for these interpretations. All right, so given that data, what could we do to write a slope-intercept presentation? We would write y equals start at 160 and subtract out 13 over and over again x number of times. Or if you prefer, y equals negative 13x plus 160. Subtract 13 over and over again, starting at 160. In an arithmetic explicit sequence presentation, where we're giving exact details about how to find the pattern in a sequential formula, we would say a sub n instead of y, the amount at time n. And that's going to be equal to starting at 160 and subtracting 13 n number of times, and replacing x with what the most of the world calls the number we don't know, n. a much more useful mathematical formula that you'll see in many of the classes that come later on. If you want it to be more accurate and say, well, what really is happening here is that the amount that we're looking for is starting at 160, and that's really the value in position 1, we should suggest that you should subtract 13 n less 1 time. 1 less time than the actual term value because we've already arrived at 13 in position 1. For a recursive presentation in section 4, in order to write a recursive formula, caveman math in my opinion, you'd have to say that the amount of time 1 is equal to 160, and to determine any new amount in this relationship, you'd have to take the previous amount, which you identify as a sub n minus 1. That means the position in the formula prior to the one we're looking for, and you'd have to subtract out 13. So it's a set of instructions, a little awkward to consider. If you were to continue the pattern in the last section of the problem, which is what the instructions had suggested we do, determine the next 4 terms in the pattern, you simply have to say, well, if I'm starting at 120, or if I'm finishing at the 4th term or 4th position at 121, and I want to find the next 4 positions, I have to subtract 13. And when you subtract 13 from 121, you get 108, I believe. That seems right. And if you subtract 13 again, I believe you get 95. And if you subtract 13 again, I believe you get 82. And if you subtract 13 again, I believe you get 69. I think I did that correctly. So the next 4 terms in the sequence would be 108, 95, 82, and 69. And that's continuing that repeated addition pattern. And again, you can imagine how in this particular sense, or based on the work we've done so far, it might not seem the most productive formula. If you did the same thing for Roman numeral 2, you'd have to identify the change in the pattern over and over again, the common difference or the average rate of change, the slope of the repeated addition pattern, which is 15. You'd have to identify the initial position, which depending upon if you're calling it time 0 or position 1, is negative 80. In slope-intercept form, it starts at negative 80, and we're adding 15 over and over again. In explicit arithmetic sequence form, repeated addition formula, we replace y with a sub n and x simply with n. Oops, mine's wrong. That should definitely be an n. That would be wrong in delta. And if we wanted to identify this as starting at position 1 rather than time 0, we would have to say that we're starting at negative 80 and we're adding 15 n minus 1 times. Sorry, variable agreement issues there. If you were to write the relationship in a recursive sequence presentation, which this worksheet is entirely about, you'd have to use 2 equations to describe this caveman math. The first equation would tell you where to start. The amount of time in position 1 is negative 80. And then you need another equation to describe the instructions on how to find any new amounts. And any new amount would be the result of its previous amount increased by 15. If you wanted to continue the number pattern, you'd simply add 15 to the last term value in the pattern, adding 15 to negative 35, and then adding 15 to negative 20, and so forth. And we could see that the next 4 terms would be negative 20, negative 5, positive 10, and positive 15 if you continue, positive 25 if you continue to add 15 over and over again. If we do a context question, which is the most important style question we could do in this class, you might see the presentation as such. If we give you 2 columns in a table of values for a repeated addition pattern, and in this case, we're describing the number of coffees purchased. That could be X. X is the number or the amount of repeated additions over and over again, or the number of times that we're making those repeated additions. And Y is the measured amount throughout time. In this case, we're measuring how much money is left on a gift card. If you wanted to determine the repeated addition pattern and you wanted to write this in slope-intercept form y equals mx plus b, you might say, Tooch, can't I just write the most popular form or formula of a repeated addition pattern y equals mx plus b? And don't I simply need to know the 2 most important variables are m and b? Isn't m often the change in y over the change in x? And if I really wanted to, would it be appropriate to label the points I've been given x1, y1, indicating the first time I observed it was after 3 purchases and there's $29.50 on the card, and then I'm observing it again after 5 purchases where there is $22.50 left? Couldn't I substitute those values into the slope formula and determine the amount of change of this pattern over and over again? You could, or more efficiently when you're working with a table, you could simply think of the slope or the rate of change as change in y over change in x. In this particular instance, what we see is that when you purchase 2 more coffees, the gift card goes down $7. For the gift card to go down $7 every 2 coffees, that must indicate that we are paying $3.50 per coffee. This must be a Starbucks coffee. That sounds expensive to me. Once you know m, you have to find b, the beginning amount. One of the easiest ways to find b, especially when these patterns get particularly long, is to substitute in for y, m, and x. We just determined m, and to get your x and y values, you can pick any point in the table. It doesn't matter if it's after 8 cups of coffee, there was $12 left on the gift card, or you could start with the beginning amount in the table. After 3 purchases, there's $29.50. You could also do this informally, and you could simply extend your table backward in time, and you could determine how much was left on the gift card after 2 purchases, after 1 purchase, and initially before you made any purchases. That would require you to undo the subtraction of $3.50 and add it back in. So if you added $3.50 back into the card, taking away one of the purchases, you could imagine that the gift card would have had $33 on it. And if you add $3.50 in again, you can imagine that that would take the gift card up to $36.50. And if you added one more, or you undid one more purchase of a coffee, you could take this card back to its initial amount of $40. Again, because these patterns get particularly long sometimes, it's just much more efficient to often use the slope-intercept formula and substitute in, doesn't matter how, any point in the table, I'll do the last one, an X and Y value. So I'll take the fact that there's $12 left on the gift card. If you're not sure where to start with formula, start with the total. So there was a total of $12 left on the gift card. And that was a result of decreasing $3.50 8 times, plus the beginning amount. $3.50 8 times, I believe, is $28. I might have to check my math there. Plus, subtracted from the beginning amount resulted in $12 left in the gift card. And if we were to add the $28 back into the gift card that was subtracted out after 8 purchases, you would see that there was $40 on the gift card initially. Same thing we get in those other investigations, whether we do it formally or informally. To write the relationship of the quantity or the value of the gift card in slope-intercept form, we would say Y is a result of starting with $40 on the gift card and subtracting $3.50 each X number of times. Or if you wanted to, you could use the commutative property of addition to reorder that. To translate that into into sequence form, explicit sequence form or formula, we would say that the amount of time n is the result of starting at 40 and subtracting $3.50 n number of times. We're just replacing y with the amount of time n, and we're replacing x with the number of repeated additions. To write this formula after 1 repeated addition gets a little funky because this actually works really well for time 0, where we haven't made any purchases, and it would get a little weird actually. You'd have to say something like the amount of time n is a result of starting at $36.50 if you wanted to describe it at time 1, and you'd have to say in subtracting out $3.50 n minus 1 times. So since I wanted to describe it at time 1, in this instance, because it's time and not a position, I actually have to say what it measures at time 1 after 1 purchase. And then I could say that I would continue to subtract out 350 n minus 1 times. As a recursive arithmetic sequence form, caveman math, you need 2 equations. The first equation tells you where to start. A sub 0. The amount after 0 purchases of coffee is $40. The second equation gives us a rule. It tells us how to continue the pattern if we were to go beyond the amount of time 0. And to do that, we'd say that any new amount is the result of taking the previous amount, a sub n minus 1. Remember, subscript is a position in the formula. So take the previous amount and continue to subtract out 350, and you'll get a new amount. If you actually continue to subtract out 350 to find out how much was left on the gift card after 9, 10, 11, and 12 purchases, you'd find out that subtracting 350 from 1250, I believe, gets you $8.50. And if you subtract 850 again from, if you subtract 350 again from 850, you get $5. And if you continue, you're going to get down to $2.50. $1.50. And if you subtract 350 again, you're going to get down to negative $2. So you actually couldn't purchase a 12th coffee there. You wouldn't have enough on the gift card. So the next 4 amounts in the sequence are $8.50, $5, $2.50, and then, $1.50, and then negative $2. You don't have enough to purchase that last coffee. There's a similar question done on a Thanksgiving can collection that's described in the context of a real-world scenario where students are collecting cans for a Halloween dance to give away to families in need. And you'd have to do the same thing if you were told it was a repeated addition pattern. You'd have to determine how much are the times changing compared to the amount of actually cans collected. So n is the number of times that students drop off cans, and a sub n is the number of cans total collected. If you were to do that, you'd find that the rate of change is 3 cans per student. If you knew that it was 3 cans per student and you wanted to find out how many cans were collected prior to anybody coming into the dance, maybe one of the teachers was collecting it during the week, you'd have to substitute in for y, m, and x to find the beginning amount b. It doesn't matter which point in the table you choose. If you chose that after 40 students arrived, there were 340 cans, you'd put the total amount in for y, the rate of change would be 3, and x would be the amount of students that had showed up to the dance. So we would assume that if 40 students showed up with 3 cans apiece, they would have added 120 to the beginning amount. If we subtract out the 120, we could find out the number of cans that were already collected prior to the dance beginning. With that information, knowing m and b, we could take that and we could write a slope-intercept form of the relationship. Y equals 3 cans per student starting at 220, or start at 220 and add 3 cans per student. If you wanted to, you could start to replace the variables with more real life or contextually appropriate letters. So F might be the amount of food, or maybe C for cans, and that's equal to 220 plus 3 per S student. If you wanted to transform that into an explicit sequence formula, kind of the way the rest of the world and the rest of mathematics looks at it, you wouldn't call it Y, you'd call it the amount of time N. You wouldn't call it S or X, you'd call it the number of repeated additions, N. And that's all you'd have to do for a recursive sequence formula. If you wanted to describe it at time 1, again, because this is time-based, it'd be a little weird to call 220 the position 1. It would actually be time 1. And for it to be time 1, you'd have to actually come up with the actual amount that was at time 1, which is 203. And then you could say from there you should add 3 cans per student n minus 1 times. N minus 1 indicating that we'd have already added in 1 repeated addition. Based on this particular worksheet, the amount at time 0 in recursive sequence formula is 200. Recursive sequence formula, caveman math, requires 2 equations. One to tell you where to start, and another instructional equation to tell you what to do. The instructional equation says that any new amount is the result of a sub n minus 1, meaning the previous position's amount, plus 3 more cans. If you were to continue the pattern beyond the table, you'd have to know that 508 was the last amount collected, and for each student that trickles into the dance late, they're going to add 3 more to that total. So adding 3 more to 508 would bring us to 511, 517, 520, and then eventually 523. The last question on this worksheet gives you some information about amounts or times within a formula, a repeated addition pattern, and wants you to come up with the appropriate arithmetic sequence. To come up with the appropriate arithmetic sequence based on the fact that after 3 repeated additions we're up to 39, and after 7 we're up to 55, the most important thing you could do is label a sub 3 x1, y1, and label a sub 7 x2, y2. And if that freaks you out, you could extract out the information and write it in a more familiar presentation. So you could say that after 3 repeated additions we're up to 39, and you could say that after 7 additions we're up to 55. So you could write it as 2 points in time. If you wanted to determine the rate of change, you'd label your points x1, y1, and x2, y2, and use your slope formula. You're not wrong if you wanted to make a mini table and you said, Tooch, why don't I say that after 3 units of time, it was 39, and after 7 units of time, that went up to 55. That might be more appropriate because then you could simply find the change in y over the change in x, and that might be easier for you to work with. But assuming you use the slope formula, you'd have to do y2, which is 55, and subtract that y1, which is 39. So our number pattern went from 39 up to 55, which is a difference of 16. In the denominator, you'd have to do the difference in time. The final time it was measured was 7, and the beginning time it was measured was 3. That's a difference of 4. Because it's going up 16 measured amounts every 4 units of time, the rate of change is in fact 4. Once you know the rate of change, you need to simply find the amount at time 0. Tooch, could I do that informally? Would it be cool if I just said that after 3 units of time there was 39 and we're supposed to add 4 over and over again to this repeated addition pattern? And can I simply work backwards to time 0? Wouldn't that be a correct algebraic technique? And of course it would. So if you subtracted 4 out of 39, you'd get 35. Undo addition with subtraction. If you subtracted 4 again, you'd get 31. And a third subtraction of 4 would get us back to time 0, where it appears there was 27 of whatever it is we're measuring in this repeated addition pattern. That would be our beginning amount. More formally, you'd write y equals mx plus b using a formula. You could pick either point in time, doesn't matter which one. I'll stick with 339. The total amount was 39, which was a result of going up by 4 over and over again 3 times from the beginning amount. So it appears as though we added 12 to the beginning amount, which resulted in 39. If we undo addition with subtraction and we take 12 out of the beginning amount and 39, we end up at 27 as the beginning amount. As a linear relationship in slope-intercept form, we say y equals start at 27 and add 4 over and over again, x number of times. To translate that into an explicit arithmetic sequence formula, most of the world doesn't call x the number they don't know, they call it n. So y would be the amount after n number of repeated additions. We'd start at 27 and we would add 4 n number of times. For this repeated pattern, it's a little bit tricky because we're trying to determine should we call the beginning amount the amount at position 1, or should we call the beginning amount the amount at time 0. Position 1 has a measured amount. It's really not up for debate. It's not as though it's being presented to us as a list of numbers. The position or the amount at time 1 was 31. So to write it at time 1, we'd have to write the amount of any position in this number pattern. If we think about it from time 1, would be start at 31 and add 4. But since we're telling you the amount at time 1, we'd have to say that 4 has been added 1 time. So we would add it n minus 1 times. A little tricky, I know. We'll work on it and it'll make more sense as we move forward. In recursive sequence form, what this relationship, or what this lesson is all about, you need 2 equations to describe that caveman math presentation. The first equation tells you what to start at. So you could say the amount of time 0 is 27, or if you prefer, you could actually say the amount of time 1 is 31. Doesn't really matter. But the second equation must give the instructions of how to continue the relationship. And that would suggest that any new amount in the pattern is a result of a sub n minus 1, meaning the previous amount, increased by 4 over and over again. And you can imagine that if you were at 39 and you increased by 4, you'd arrive at 43. And if you increase by 4, you'd arrive at 47. And if you increase by 4, you'd be at 51. And if you increase by 4, you'd be at 55. So the next four amounts in this number pattern would be 43, 47, 51, and 55. Ladies and gentlemen, this is the lesson on recursive repeated addition sequence formulas. In sequence formulas, we typically trade x and y for a sub n and n. And in a recursive pattern, you need two equations to describe the repeated addition pattern. It's caveman math. It usually comes first. I find it a little awkward, so I do it last. We need one equation to describe where to start the pattern and a second to give a set of instructions. Hope that makes sense, and I'll see you in class. Take care.